Okay, welcome back, everyone. Let's see. There's Pontus. Hello, Pontus.
Hi there. How are you?
I'm well, thank you. I hope everybody's had a good break. I know that being at Zoom too long makes me a very unhappy person. So these breaks are a good thing for all of us. I believe you're going to get started with the first part of this discussion. Yes.
Yes.
All righty. So many of you know Pontus. Pontus is a principal professional staff at APL. He is the instrument lead on, is it one or is it two instruments on their way to Europe at the moment?
Two sensors.
Two sensors on the Jupiter Icy Moon mission. And he's been our project scientist from the beginning of this study effort. Elena Provornikova is also joining us this afternoon. Thanks, Elena. I see you're here. And Elena's,
hi, Michael. Yes.
Hi.
I'll support any questions during this hour.
So. Very good. As our heliophysics lead, it's very important to have Elena here since first and foremost, as we all know, this mission is about the space and solar physics decadal survey, heliophysics returns that can be made by a mission that accomplishes this, as well as in situ measurements of the interstellar medium. And so to have the pair of them presenting this is fantastic. Thank you both for preparing all this. With that, I will get out of the way and off you go.
Okay, well, thank you very much. Yes, so Elena has had a parallel, very important meeting as well. But I'll take the most of this discussion and most of this presentation here, and Elena, you can jump in as necessary and correct me where I may go wrong. So let me start this off and say this is where we all get together and talk about the compelling science case for this. This is what Ralph alluded to in the beginning, one of the four pillars of how you go about to get a mission to the launch pad. Another important aspect I want to bring up here that people tend to forget, I think, but it's sort of deeply rooted. It's this notion that Jim presented, and that's the pragmatic solution to system engineering, and so having that sort of demonstration of that this is really something that is possible is extremely stimulating to scientists, because then all of a sudden we spring into action, right? And at least that drives me very much here. So I do want to thank all the scientists here. I think we have now probably up to 100 or so pretty active scientists working on this. And in the days to come here, we're only going to give you a brief sort of overview, map of the landscape, if you will, and where we're going with it and the actions. So in the next coming days, listen into the topical group discussions of the science leads. This is really where we would like to see your input and engage in the discussions. Also, I would like to encourage all the scientists to also engage in the engineering discussions, because this is really a mission where this iteration between mission systems engineering and science is more important than ever, I will say, just because of the nature of this mission. All right, let me go to the next slide here. You've seen this slide before. These are the goals that have been hanging out there for quite a long time, ever since, I say, at least back to the 70s. The primary goal, as you already know, revolves around our star, and our star is this one star in our galaxy that plows through that interstellar medium and carves out that magnetic bubble that we live in. And alluding to Alan Stern's comment, a very perceptive one, may not be the only habitable one, but it is sure indeed inhabited, of course. And really the mystery out here is what makes this boundary. There are a lot of unique interactions here that really makes these questions the most outstanding questions of space physics today, I believe. And then, of course, beyond the heliosphere, passing the boundaries out, beyond the heliopause and out there, that's really where this unexplored sea or this unexplored local interstellar medium presents itself. It's a completely new territory, and it's also not only decisive for the entire heliospheric interaction and what shapes the heliosphere, but it's also that key for understanding, you know, our home in the galaxy, where we live in this bubble and how it all interacts, right? We've also been asked by NASA to look at the supporting goals and assess any science values out there on an outward trajectory, any science values towards planetary goals and astrophysics goals, and they're certainly out there. So on this outward trajectory, it's very clear there are plenty of opportunities for both planetary and astro, with relatively modest contributions we come to find. I don't really have time to go into detail. I'll spend maybe a couple of slides on it here, but topical groups led by Kirby, Abby, and Casey will discuss this much more in detail later. I'll say this about the KBOs, of course, and I think Bill McKinnon, he put it very nicely in one of the workshops where he said, for any heliophysics goal, there is one out there for you. In terms of KBOs, there are over 130 KBOs out there. So the other for astrophysics is this notion of carrying an infrared detector to look at the extragalactic background light and also the circumsolar dust disk. Okay, so let me jump into the map. You've seen this before, but I'm going to repeat it. This is in a logarithmic scale, starting with the sun and going out beyond the Oort cloud at about 10,000 AU. And you'll also see Alpha Centauri indicated here, of course, but we are not going to Alpha Centauri, as we already established. There are two accidental explorers out there already. It's Voyager 1 and Voyager 2, as we know. Both have crossed the heliopause. And as was talked about earlier, we're within this framework of trade space that is bounded by the 1000 AU, being able to operate at 1000 AU, but within a design lifetime of 50 years. Those two are independent requirements. So it's not like you're going to divide those numbers to come up with this speed. This is the trade space that we're working within, the pragmatic trade space, if you will. I'm going to start with the very basics here, because we have, I think we have close to 100 early career participants, maybe more. So go up to your kitchen sink and turn on the faucet, and you'll see this pattern arising pretty quickly if you have it set up right. And here in the middle, of course, that is signified by the sun and its expanding solar wind. But our sun, as I said, it's plowing through the local interstellar medium with about 24 kilometers per second. So when this expanding solar wind meets the apparent flow of the very local interstellar medium, a couple of things happen. Of course, in the inner boundary, you create a termination shock. And this is really where the solar wind speed is terminated and it goes subsonic. And it creates this shock-like structure, right? And then beyond the termination shock, we have what we call the Heliosheath. That is what contains that slowed and shocked solar wind plasma that flows outward and bends around in the Heliosheath. Outside of that, the heliopause, that is the theoretical boundary where the solar wind really stops. And this is where the local interstellar medium properties take over. And that really is represented by the pressure balance between the bubble and the local interstellar medium. But as I'll talk about later, there are a lot of surprises there from the Voyager missions and their limited measurements. So all in all, this hydrodynamic picture, it's very intuitive, maybe very attractive, but after all, remember, this is just a sink, okay? The whole thing that makes this extremely interesting is the notion that we have interstellar gas, interstellar neutrals out there that do penetrate the magnetic boundaries of the heliosphere. And when they get in there, they of course, they photoionize and they get picked up by the solar wind. And this is what we call the pickup ions. And once they are picked up by the solar wind, they're being brought out into the boundary again, where they mediate the characteristics of the boundary. So already very deep inside the heliosphere, you start forming this boundary, if you will. So that's why it's so important for us to not only go to the boundary and measure the boundary, but also measure it all the way out to understand this entire beast. Of course, Voyager 1 and Voyager 2 are out there. They have traversed the heliopause. So we, together with Voyager 1 and other missions like IBEX and Cassini and Ulysses and SOHO, we do know a lot about the heliosphere. I mean, I'm not going to shy away from that, but the more we look at it, the more we understand that we're really only scratching the surface of this completely new regime. Voyager 1 and Voyager 2, they, as some of you know already, they were missions dedicated to planetary exploration. It was the planetary flybys that brought them to the interstellar medium today. They will live for about 4 or so more years until their power levels drop below the critical levels. So Voyager 1 will really have reached only to 170 AU approximately. From inside this bubble, we have, of course, IBEX and Cassini. They've imaged these boundaries, looking out, inside out. And to date, I think it's fair to say that they have brought the best global understanding. There are observations also including SOHO Swan, of course, and also from Ulysses, the gas experiment, and New Horizons. They have further brought us remote information on interstellar neutrals and how they interact with the heliosphere. Upcoming mission, IMAP, that a lot of you have heard about and are also very involved in, will really provide this order of magnitude better imaging capabilities from inside the heliosphere. And this is really critical for us because it really will guide the further formulation of an interstellar probe, and not only where we're going perhaps, but also the nature of the science questions, I believe. Okay, so I'm going to go through all of the goals and all the objectives in a very high level here. So my purpose here is to sort of provide you a map, if you will, so you can better navigate the topical group discussions later. By the way, these slides, they are on the website already. You can go to the meeting website and you can download the PDF from there. So let's start with the first one. And this one has always sort of been on the top because it's really the uniqueness of an interstellar probe, not imaging, but actually going there. We're going through the inner heliosphere to that boundary and into the interstellar medium. And so we do the in situ measurements, but we're also imaging at the same time, right? So that's really the uniqueness. The one easy to understand on the top here is, of course, the shape. What does it look like? We do have the boundary determinations by the Voyagers, but the interstellar probe would also determine the boundary at the third intersection point, while also doing the imaging. The second one here is really about the physical processes, and that is really what makes interstellar probe unique. We think it's really this idea of determining these physical properties at the same time as you try to understand how those physical properties manifest themselves globally in terms of the shape. So for the force balance, many of you know already, that critical energy range that upholds this shell of the bubble, it was never directly measured by the Voyagers, unfortunately. It has been inferred from other measurements, from imaging measurements inside, and also extrapolations, that it's really the heated pickup ions that plays most of the dominating role of upholding this bubble. But all in all, we've never had direct measurements of even this basic feature of how this bubble is upheld. The termination shock was a big surprise, the Voyager. There were a lot of predictions, but of course, it's fair to say that this shock is a completely new type of shock. The plasma properties when we went through the shock were completely unexpected. So going back and really understand how that shock is formed is of critical importance here, of course. The heliopause, a lot of us expected a certain kind of shock, and a smooth shock perhaps even. And also more importantly, the interstellar magnetic field. Once Voyager 1 and Voyager 2 crossed into the interstellar medium beyond the heliopause, the direction of that interstellar magnetic field, or of the magnetic field measured, didn't really change. It still had this solar-like direction. So it indicates that the magnetic field topology through the heliopause, through the boundary, is extremely complicated, and it's not yet understood today. The fifth measurement objective down here, or a science question, is about the interstellar neutrals and the pickup ions, and goes back to what I said from the beginning, that this boundary is really formed even deep inside the inner heliosphere. That's where the physical mechanisms and processes helping form this boundary starts occurring. So measuring interstellar neutrals and the evolution of pickup ions as you go out is extremely important. Second science objectives pertains to the dynamics, if you will, and a lot of these science objectives are carried through from previous versions of the science traceability matrix from previous studies. So we sort of left those alone. So this is about the dynamics and how the sun affects the boundary, and also how the interstellar medium and its possible inhomogeneities also affect the global heliosphere. The first one, solar wind effects, of course. How does the Heliosheath, how does the termination shock and heliopause move throughout the solar cycles? And to your right here, you see ENA images, both from IBEX and also from Cassini, over a long-term trend, where you see these correlations of imaging between imaging and also the in situ solar wind properties. The other one is about shock propagation, and also connected to that is how shocks propagate beyond the heliopause. Voyager 1 and Voyager 2 has seen shock propagation very, very far up from the heliopause. And this circles back to this whole question. Well, how far is really the extent of the heliosphere? How far does it go? We don't know that yet. The third one here on the list is the famous galactic cosmic rays. The galactic cosmic rays, they are created somewhere in the galaxy, but at the heliospheric boundary, the heliospheric magnetic boundary does shield it, and it shields it with a modulation, because this entire system is breathing, if you will. We do know that galactic cosmic rays, they have an important effect on atmospheric chemistry that may tie it back into habitability. So that's one of the other links in trying to understand the shielding of galactic cosmic rays, and perhaps how that is affected and works at other astrospheres. The fourth science question here is very compelling, but it's equally hard, and we need your ideas, we think, in this. And that is, what are the effects of the local interstellar medium on the heliosphere? So to your right, bottom right here, we show the effects of different interstellar medium properties, and how that dramatically alters the entire shape of the heliosphere. So trying to understand this by understanding and determining the detailed physical properties out there is one of the groundbreaking discoveries that we can make. And that is also very important for understanding where the heliosphere is going in the local interstellar medium, because the heliosphere is plowing through the galaxy, as we know. Which brings me to the third goal, and the third objective, I'm sorry. And that's, once you get out there and discover and quantify directly the properties of this unexplored, very local interstellar medium. So as I said from the beginning, this is really where this new territory awaits. To give you a background of what we know today, all the knowledge that we have of this unperturbed local interstellar medium are the average basic properties inferred from absorption spectra towards the nearest stars, and also from measurements, of course, from interstellar pickup ions and dust and other things penetrating the heliosphere. So it's a very average picture that we have. You can see an image or a sketch, an illustration of the neighborhood from Linsky and Redfield in 2019 in your upper right here. And it turns out that we do believe that the sun has graced the green local interstellar cloud about 6,000 years ago. And I think that was a finding from Priscilla Frisch a while back. But also it continues, of course. And depending on who you ask, it seems like we're already outside of the local interstellar cloud. But all in all, it seems like we're in touch with no less than 4 interstellar clouds. So in a sense, this is a galactic event. It's very timely. This is a galactic event taking place on, of course, thousands of years timescales, but it makes it more urgent for us to understand really how the heliosphere is shaped and how it alters depending on the interstellar environment that we're in. Excuse me. Okay, so we have a range of science questions here. I'm not going to go through them all. Of course, the bow shock is what is beyond the heliopause, we believe. It has not been detected, but we sure believe it's there. But the true nature of it is still unresolved. The hydrogen wall is this blanket of hydrogen beyond the bow shock, probably up at 300 AU or so. That wall is critical for the formation and for this charge exchange and how interstellar plasma and gas interacts to form all of this. There's, of course, the filtration processes. Basically, how does neutrals and gas and dust, interstellar dust, how does that composition change as it penetrates the heliosphere? And you'll see this particular sort of science question. Another side of that will pop up under the astrophysics objectives as well. Whole range of other ones. I'm going to pick on one. The last one here is the inhomogeneities. During the 50 years that we will be out there, is it possible that we would actually detect gradients or inhomogeneities? It would be a groundbreaking discovery if we did. And that is something we would like you to think about as well. We need your expertise here. And then the very last one is, of course, the galactic cosmic race and its origin. So let me talk for a few minutes on the supporting goals. The first one here is, of course, KBOs and dwarf planets. There are 130 dwarf planets, and I think Kirby may actually correct me on this later. And there are more than 4,000 KBOs projected to be out there. So this solar system that we live in, it's only the beginning. And it's easy to understand that any direction we pick from heliophysics, defined by the heliophysics goals, and of course they are not precise by a degree, but they can vary by a couple of degrees, maybe up to 10 degrees. That offers at least one compelling flyby to really understand the origin and evolution of planetary system. There are a range of questions here, ranging from the current state of evolution that pertains to geophysics and composition of these KBOs and dwarf planets, but also there's the collisional or orbital geological history, atmospheres, and since we're flying by mission design, flying by Jupiter, there's a ton of science, even if it's a very short flyby. The next one I'm going to talk about is the circumsolar dust disk. So this is the remnant from when the solar system was formed. And at the bottom here, I showed the dust disk of the star HL Tauri. And what really was amazing when people looked at this image, and this is an image that was collected by the ALMA radio array, it's a ground array. You look at it and you say, wow, there's a lot of structure in there. And then you look closer and you go, oh my God, that's azimuthal structure. And that's an indicator that there's planetary formation. And then the real shock comes when you determine the age of this thing. It's 1 million years old. And some people argue it's even less than that. So is this really a solar system infant? So that's sort of the beginning stage, and it's revising the formation theories of the solar system. The end state to your right here, that's a simulation, or best guess, by Andrew Poppy in his paper, that was driven by also the New Horizons dust counter detection. So they do have a little constraint on the dust count profile, not composition. But there's never really enough data to simulate this accurately. So being able to measure dust, the composition, but also going out there and look at the infrared emissions from this dust disk beyond the zodiacal cloud, through the zodiacal cloud, is extremely important for providing the ground truth for planetary formation. The third big one here is, of course, exoplanetary analogs. We started discussing this already in the first workshop. And it's a very simple idea. I mean, with the backdrop of all these observations of other exoplanets and exoplanetary systems out there, is there something we can do by looking back and looking at the solar system as an exoplanetary analog? And what we're talking about here are, of course, phase curves, maybe transit spectra, and other things that would be extremely valuable to better help characterize exoplanetary observations. Okay, so the last supporting goal that we have here comes from astrophysics, and again, it gets back to the infrared emissions, and the infrared emissions are part of the energy release of the early universe. But yet we're sitting inside the zodiacal cloud, and of course this zodiacal cloud emits in infrared, so we can't see what we call the extragalactic background light. And this extragalactic background light, or EBL, is all the integrated light from all the galaxies and stars that were created from about 200 million years after the Big Bang. And it's a redshifted light that appears in this wavelength range. So just by going out tens of AU through the zodiacal cloud, that foreground emission will already start diminishing, such that you can actually make good spectral measurements of this EBL. And as the further you go out, the better it will become. Okay, the other one is interstellar dust grains. So this is really where we get into interstellar dust grains being the sort of galactic messengers, if you will. It's by measuring the composition, and also maybe its isotopic composition beyond the heliopause, the unfiltered composition. One may be able to actually take a look at galactic chemical evolution as well. And I believe tomorrow or Wednesday, Casey will talk more about this in depth. The other ones out there is of course, if there's recent nucleosynthesis out there, just by going out and doing in situ measurements of isotope, of the usual suspects of isotopic ratios, as I've listed here, and perhaps even making constraints on cosmology and Big Bang. That is all hanging out there. These are not new type of measurements really, but it's really enabled by a probe going to a completely new place. And that's what's really compelling for this mission. Okay, so let's roll up our sleeves and talk about the purpose of this trade study. I know it's been talked about before me, but again, it is a trade study. It's here to provide NASA with a menu of options and trade-offs. After one gets a higher priority in the decadal survey, NASA may decide to establish a science and technology definition team, and their task is to define a payload and define a mission scenario to which the mission shall be designed. So that is not our job. This study will provide that definition team with that necessary menu of options and analyze trades within this pragmatic space. So we're sort of laying up and preparing their work. We're preparing the work for them. And I've seen this in a lot of the communications and email threads out there. This is not a proposal. So please remember, not a proposal. There is no concept here that will win over another concept. This is all where we put out on our creative hats to make sure we're covering all the bases and really documenting the trades out here. So what do we need you to do? We need you to formulate the compelling science objectives and questions. We've done that over the 2018 and 2019 workshops and in between. And of course, identify those mature measurements, comes back to pragmatic and the methodologies that can achieve the science. And then very importantly, document the trades between all these different options. There are reports out there, and there is going to be one big final report as well that a science definition team can pick up and look at all these trades and all these menus. And of course, reach out, write white papers, support the decadal survey. So in the end, it's you that make an interstellar probe reality. Okay, let me check my time here. So let me speed up just a little bit. The purpose of this third workshop, of course, communicate the latest development in mission architecture. Jim did an excellent job of that, and we'll hear more about that as well. Discuss and collect the community input. I'm going to go through briefly the science traceability matrix, mission success criteria, science operations, example model payloads, and again, document trades. You've seen this, if you're signed up, you've seen this in previous emails from me and the team. And really at the outcome of this workshop, as we see it, we want to reach some level of consensus so we can finalize a complete science traceability matrix not long after this workshop. And then in the fourth workshop in 2021, hopefully in person, we will target to demonstrate that we have closure, that we have a complete concept that actually closes and we can move forward with. So to coordinate all these inputs, and believe me, we got a lot of inputs, please participate in the topical group discussions and work through the topical groups. And then on Friday, what we will do, we will collect as much as we can of all this input and formulate a summary and also the next steps and goals. So if you have any ideas, you have any tweak to what we're doing, please bring that up in the topical group discussion so we can do a course correction if we need to. Here's the brief org chart, so you know who's who. You've seen a version of this before. What I want to convey here is on the right side of the screen. This here, the dark blue box here, that's really the community. That is you. So what we've chosen is to construct these number of topical groups, and they're really organized around instrument types or measurement types, if you will, because that nicely segues into the science traceability matrix. You can look at these names here. Feel free to shoot me an email if you're not on one of those groups and you don't know the people. We're here to help and here to get you engaged. So with this, we want to trigger you to start thinking about this, and we think this is a good way. And I think Alice will scold me later for butchering the French language, but these are really the interstellar probe raisons d'être. The first one here is the design lifetime, and of course that's within the pragmatic engineering trade space and driven also by engineering requirements. But what are really the scientific reasons, and what are the success milestones along the way? Why 50 years from a science perspective? And of course that ties into distance. Minimum distance, for example, what's the minimum distance that we need to go? 250 AU is sort of what we're carrying right now, and that came about from well, it's beyond the Voyagers, and it sure puts us well beyond the Heliopause. It may put us through a bow shock and maybe start looking at the hydrogen wall, and also it loops back to the minimum distance for capturing this ENA image or image externally, where we can definitely discern the shape of the heliosphere. So you can look at this at your own leisure. there's of course the same type of argument for the speed. We're currently at 7.6 AU per year. That gives you about 4 or 5 years through the Heliosheath, which is a fraction, a significant fraction of the solar cycle. And that is needed when you penetrate the boundary. You want to see the dynamics. You just don't want to plop through it in a couple of months or just a year. That would make the scientists very unhappy. So a lot of these thoughts, we want you to spill your input and your comments in it. We've started a Google Doc here, and you're free to log into this and comment as you will, and we're trying to collect all of this information. And as I said from the beginning, this is really to help you start thinking about this and funnel your creativity. Okay, Science Traceability Matrix. A lot of you already know this, but it's Science Traceability Matrix is the ultimate focal point. It takes the entire flow down from science through the required measurements and methodologies to closure and also mission requirements, of course. So it's really this translation from science to implementable engineering requirements. And I'm underscoring implementable here. Of course, we can't have a science traceability matrix where the answer is something that cannot be achieved. So that's why this iteration between Jim and his team and the project science team and the community is very much important. Okay, so this can be challenging. We have over 100 people probably looking at this. So we're trying to do what we can to funnel and organize all of this input. So as I said, it's not complete, but we do need to reach some level of consensus so we can have it complete after the workshop. So what has changed since the previous workshop? We have 40, probably 50 comments already from the community. Thank you very much. No major changes in the measurement requirements have really been seen. There are tweaks and details in there. And also, of course, the nature of the science objectives hasn't really changed over the decades, of course. But many of the science questions, not objectives, but the science questions, there's been some new ones, and they've been motivated also by new observations. We added 3 phases and divided our thinking into 3 phases: the inner, outer, and heliospheric phase, and the interstellar phase. We can certainly discuss those definitions, but that is the first start of trying to organize how we think about moving from the inner heliosphere out into the interstellar medium. Here is the traceability matrix and all the columns that we have. The link you should have seen already. If not, it's here. It's a Google spreadsheet. It's quite large, but part of the intent is also to try, in this large spreadsheet, try to document everything that we're doing, which is really important. And I'll show you a very condensed version of this. There's been a lot of comments on the flow down and the name of the columns, as usual. We have goals, science objectives, which is really what we want to determine, and then specific questions of what we want to answer under each objective. Then that flows down to the measurement objectives, or methodology, if you will, and then measurement requirements. These are the quantitative requirements to which the instruments have to be designed. Then we've divided it into the 3 phases that I'm talking about, and this is really where we want to make the measurements. We have a detailed approaches column that you'll see in the spreadsheet, and that's quite lengthy, but the intent here, that's sort of the catch-all column, and this is where you'll see a lot of references and detailed investigations that will back up what we have in the traceability matrix. Of course, I mean, these columns can be hidden when we show them, but it's part of this documentation exercise. We really would like to keep it there. And then down to measurement requirements, analysis products, and last but not least, closure. And closure is really, once you have your spectrogram, once you have your image, what do you do with that data to answer the science question? That's how we define closure. We're not there yet. A lot of these fields are still missing input, so we need to finalize this very soon. We have also worked on mission success criteria. We have done this because we want to inform the mission, how it's going to be designed, and specifically the fault tree analysis. You see Clay Smith will talk about this later. And that fault tree analysis was used on Parker Solar Probe, and it in turn, it feeds into how we think about redundancy. So let's talk about baseline and threshold mission success criteria. The baseline mission success criteria, those are the requirements to which the mission shall be designed. Ultimately, this will be the full STM. We're not quite there yet. We got to make sure to streamline it a little bit more. Then we have what we call the threshold mission success criteria. And those are the minimum set of requirements that makes the mission still worth launching. And note here, this is worth launching. And this is a decision that usually takes place before launch, right? So to get ahead on this, we've constructed example threshold mission success criteria. So you can see more of this on Wednesday. It will be a pretty interesting discussion. You'll see the outcomes of redundancy. I don't think there will be much surprises here. The way we're thinking about this sort of follows what we also done Parker Solar Probe. So we want this to be achieved by answering at least 2 science questions under each objective. And under each objective, you want to meet at least 1 priority 1 measurement objective. And you'll see this once you log in and look at it. And why we're taking this approach, it's a good approach, we think, because it really allows for this range of different scenarios. It doesn't really just lock us into one scenario, and this will be mission success or nothing else. It gives us flexibility. So it allows for these sort of different sets of measurements to accomplish threshold. So keep that in mind as you enter these topical group discussions. Okay, here is the very condensed science traceability matrix. It's very similar to what Ralph already showed in his overview talk. We have the 3 objectives. It's the physical processes and the global manifestation, dynamics, and then the unexplored very local interstellar medium. We can show this a different way for your reference. It's the same questions, of course, but here we have divided up in terms of the instrument types. And the color code here shows you where it's needed and required. And the dark green is the inner heliosphere, light green is the outer heliosphere, and then orange is the interstellar medium. So if you back away from the screen a couple of feet, you'll already see sort of a pattern arising of what is really needed here. And to some, I don't think that's really a surprise here. Okay, very importantly, understanding of the allocation. This is a picture from what I presented at the 2019 workshop. So currently we're studying an intermediate payload mass of about 80-90 kilograms. So where did it come from? It's the allocation between previous missions. Voyager was over 100 kilograms, 107 or 110 if I remember correctly. Parker about 50, and New Horizons, of course, tiny, 30 kilograms. So sort of a sweet spot we want to stay with. So why are we fixing it? These example mass allocations. Remember, these are example mass allocations. Well, first of all, it enables a realistic exercise in actually documenting these science trades. And it presents, again, a future definition team with this realistic scenario of what they may have to look at, right? And it sets up also a process very early for avoiding this infamous Christmas tree that had killed many mission proposals out there, mostly because of cost. Everything just escalates out of control. And perhaps more importantly, it provides also the decadal with options. We have a bucket, but we can debate later what exactly to put in that bucket. But we're documenting the traits of what to put in that bucket, right? So some decadal concepts have seen this sort of all or nothing approach, and we really want to avoid this all or nothing approach. We want to stay flexible and give them options here. Okay, operational scenarios very quickly. Jim already talked about this. We have the heliophysics baseline that we're studying right now. The augmented payload, the 3-axis dual mode, will be studied sometime next year. And there are other scenarios that I think also Kirby will start talking about. This is the so-called nose camera and what that could possibly give. And do remember, we did discuss this last year, and that was the scenario where we discussed of do the KBO flyby first, and then spin up the spacecraft and centrifugally deploy your 50-meter wire antennas. And I can feel Gabe cringing right now. And we discussed this at some length during the last workshop, and we quickly decided this is too much of a risk for the mission. And again, this will be documented as a trade. You saw this before, baseline scenario, under study now, spin stabilized 50-meter wire antennas. We have the inner heliospheric phase, where you sure as heck is going to do measurements throughout this phase, through the outer heliospheric phase, 70 to 250 AU, and then in the interstellar phase, and then the augmented one, which is next to study. Baseline trajectory, really quickly here, we did pick back in 2018 a notional example direction, and that was 45 degrees off the nose direction, and roughly 45 degrees off the nose direction, because it gave you the physics that you want to have by going through the nose. This is where the action takes place in terms of force balance, in terms of pressure balance and things like this. But also it sort of intersects a ribbon, which is this enigmatic feature that IBEX detected. And thirdly, 45 degrees is roughly enough to get sort of a side view of the heliosphere to discern uniquely the shape from ENA imaging. There were at least 5 other options that were discussed. I have listed them here. It was from the nose, tailward, off ecliptic, and other options that we discussed. And again, this is about documenting the trades, and what we have now to drive the mission architecture is this optimized example baseline direction. It's not strictly in the ecliptic plane. We nudged it down by about minus 12 degrees to optimize the speed to the 7.6 AU per year. Wayne will talk about this in more detail later. And again, it still fulfills the heliophysics objective. Remember, this is example direction that is needed for the mission system engineering team to go ahead and study this. All right, let's jump into the subject of the example model payloads. And again, remember, this is the 80 to 90 kilogram bucket that we want to fill with good and valuable instrumentation. It's not the decision. It's about trying to document what are the science trades of what you put in this bucket. You'll see there is the magnetometers that Jim already mentioned, plasma waves, the 50-meter wave antenna, the plasma system, yes, with composition, and in particular, the plasma measurements are extremely important, because Voyager had a very limited plasma measurement that has really hampered the interpretation of the data. Energetic particles, the cosmic ray system, interstellar dust analyzer, as I talked about, neutral mass spectrometer, an ENA medium detector and telescope from about 0.5 keV or so, and then a high ENA imager from several keV up to about 100 keV to take a look at that entire energy range, and the Lyman alpha spectrograph to take a look at the interstellar hydrogen. I know there are several strong opinions out there what to fill in here, but the important thing here, as I alluded to before, it's really keeping this bucket fixed. And and give examples and document why a certain instrument should be there and why another instrument should not be there, and how we trade those off with each other. I do have a pie chart here because it did sort of weigh in, at least to some external participants, that from a 10,000 foot view, you want to sort of see the apportioned measurement types. Charged particles is one of the big ones, of course, as is fields and waves, which is about 20 some percent each. ENA imaging is already up at 25%, which is, of course, due to the heavy instrumentation as well. So that's a very good guide. This is for your reference. You can look at this since I'm running out of time. This is the first sort of iteration of an accommodation in a nice rendered version. It's not completed yet, but please take a look at this. It's in the slide deck. Then we have the notional augmentation from planetary and astro, and this is pretty simple. Some of the instruments were swapped out to stay within the 80 to 90 kilogram bucket. And those instruments are, of course, the flyby cameras, UVS, and also the visible near infrared for the flyby images and composition. And then for the astrophysics side is this infrared mapper that we're talking about to look at the zodiacal IR emissions and also the extragalactic background light. Coming up to the end here, data volume and communications. We need to talk about the sufficiency. Peter Coleman sent out this Google document to you all and to the topical groups. The way we started out with this, of course, is the bucket out here. And please look at Dave Copeland's discussion later about how these buckets were determined. We started off in the inner heliosphere with pretty healthy rates, so we're not too worried there. But when Peter put this table together, he looked back in history to see what the notional rates are there for other instrumentation. It looks pretty good already. Of course, we're above with ground stations and the 5 meter dish. We're already above the Voyager rates, of course. But please work through your topical groups to make sure that we're not missing anything. We want to hear if this bucket is enough to make the compelling science. We're already predicting and assuming future ground stations such as the NGVLA and things like this to come up with these rates. Okay, I should probably stop now and take questions. My concluding remarks is sometimes we got to back up and really look at what we're doing. This is not just another mission. This is the beginning of humanity's journey into the galaxy. And I think this is really what driving most of us here. This is such unique, and we get to actually think about it and study it, and maybe one day see it launch. So we're technically, I believe, ready to take this first explicit step. It will take us to this completely new explored region of space. It's the Mare Incognitum, to understand our home in the galaxy and find answers to those questions that we can't really think about yet. And with that, that concludes my presentation, and I can take questions. Thanks. Thank you, Pontus. That was great. There's 2 questions we could take pretty quickly here. Vikas asks, with regards to looking at inhomogeneities in the very local interstellar medium, which physical quantities or observables are you interested in? Elena.
Sure, Pontus. I'll be happy to answer that question, and you can take a breath now. That's a great question, Vikas. Thank you. So the primary physical quantities that we would like to look at is hydrogen density and temperature, and also plasma density and ionization, because it's possible that there would be different regions with different, for example, colder hydrogen and kind of warmer hydrogen. We don't know, but it certainly would be a great discovery to see this kind of regions as interstellar probe goes further from the heliosphere boundary, further into the interstellar space. Pontus, do you have anything to add to this?
No, not really. That was a very exhaustive, good answer. Well, I do, but that we're running out of time. But there's of course the isotope question and the entire composition of the local interstellar medium as well, and the charge fraction as well. I think you mentioned.
Alrighty. Thanks, Elena. And Ron Turner points out that Voyager 1 and 2 went out in different directions, and comments that and any additional mission going out in another direction would again give us another distinct set of measurements. Thank you, Ron, for that comment. And Sunny Harmon asks, is there a notional downlink rate for necessary engineering signals? That is, what percentage of the 30 bits per second is allocated to science as opposed to spacecraft status? And I think we'll get into the nuts and bolts of that later in the week with the communications discussions. So if it's okay with everybody, we'll defer that question until later in the week, where Reza and Dave can chime in with some specifics about that. But I do know that they're accounting for that sort of thing. They don't forget we need to know what the spacecraft is doing.
Michael, I think that
yes.
There was a question in the Ron's comment, actually.
Oh, was it? Did I miss it? He says,
I mean, it reads to me like, to what extent did Voyager analysis, basically, does Voyager analysis point us to any specific direction where we should go?
my apologies. Go ahead, Elena.
Well, maybe I read it wrong, but this is how I read it. But this is certainly interesting way of thinking that we should probably discuss it this week. But the direction is really the trade study, and there are different directions, interesting directions where we could go. And it's really, depending on the direction, we can answer certain science questions, and going to other directions, we perhaps can miss some of science, but answer some other science questions. It could be interesting to go into the tail, but we could never reach the interstellar medium, because we don't know, maybe the tail of the heliosphere lasts for 1,000 of AU. So yeah, it's really a trade study.
Yeah, I would like to expand a little bit on
yeah, sure.
comment here. It's not only Voyager 1 and Voyager 2 that sort of informed the discussions, but also the remote imaging, of course. It seems like this nose region is where the action takes place, and a lot of the science questions that they revolve around this force balance, and going in that general direction of the nose is sort of what you want to do to be able to answer those questions for certain.
All right. Thank you, Pontus and Elena. So now we're coming up close on 2 o'clock. And just as we talked about, another question has climbed in here from Casey. Casey Liss asks, we should also remember that the role of dust in the heliosheath and heliopause could be very large, but we know almost nothing about it until we send an IDA. Somebody help me out with the...
Interstellar Dust Analyzer, IDA.
Thank you. IDA, Interstellar Dust Analyzer, through this region and into the nearby galaxy to sample pristine galactic dust for the first time directly. Thank you, Casey. Yes, in fact, that's been one of the most illuminating things to this engineer, is just how important the interaction between the dust and everything else is along the way. John Cooper asks, the higher GCR flux, the galactic cosmic ray flux in the very local interstellar medium, also means higher radiation noise background for other measurements. Will you institute a process for evaluating this on each instrument?
Yes, galactic cosmic rays, that they have to be taken into account when you design the instruments and shielding and things like this.
Very good. Thank you, John. And thank you, Casey. So with that, we will wrap up for today. A couple of notes before we adjourn. Tomorrow, we'll have a kickoff again at 10 o'clock in the morning Eastern time. And shortly after the kickoff, we'll actually break up into a couple of different rooms. And based on the agenda that you'll find on the website, you can join whichever room you choose. Tomorrow is focused on science questions. At the end of the day, 2:15, we're going to have a networking session with a tool called GatherTown that allows you to walk around a virtual room and interact with the people who are in the very local area that you're in when you move around in GatherTown. And the graphics are a bit quaint, but it's actually a quite fun tool to use and allows you to socialize a bit with the folks that are here today and join us tomorrow. On Wednesday, there will be, again, dual sessions, dual tracks, I mean. Some of them are engineering, some of them are science. And again, on Thursday, likewise, we will have dual tracks. And the poster session for the conference, for our meeting, for our workshop this week, is held in GatherTown at 2 o'clock on Thursday afternoon. And the poster session material is already up on the website. You can look at folks' posters, and I believe that the videos may also be available to watch. People put together short presentations to go with their posters, but you can find them in GatherTown and ask them more questions on Thursday afternoon. And then again on Friday, the student program is going to ramp in again, and we'll talk more with the students about what it means to plan their interests over the years as this program moves forward, as well as a general wrap up of the effort and the results of the week, but especially discussion about the white papers that we're all hoping you will participate in as we move into the next Space and Solar Physics Decadal Survey, and then updates again from the RPS office and from the SLS office, and the final wrap of the Science Traceability Matrix that Pontus discussed, and next steps for all of us as a team. With that, thank you all so much for being here. Pontus, I love your enthusiasm at the end. I love how you keep bringing this discussion back to the fact that this could be one of the most exciting exploration missions that any of us ever gets to work on. And it's one that we can pass down to the next generation as we all move through our careers. It'll last longer than any of us. It's fantastic to be part of this. And I look forward to seeing all of you tomorrow. Thank you all very much.